working on related rates, and a related rates problem involves multiple variables that all change with respect to some other common variable. Time is usually that other common variable. So for example, if you watch a firework soar off into the sky and blow up from a little spark into a great big ball, that creates a situation for a related rates problem. The volume of the ball increases with time. The radius of the ball is increasing with time, and very dramatically. So when you're doing a related rates problem, you first need to come up with the formula that relates all of your variables. In this case, volume and radius are both related to time, and so the volume of a sphere would be the appropriate formula. Then, once you get your formula, you take the derivative of both sides, remembering that each of the variables is a function with respect to time. So you're going to have to remember to do the chain rule. On this side, I just have v to the first power, so the derivative will be dv dt. 4/3 pi is a constant multiple that just gets carried along. Then I use the power rule and I take the derivative of r cubed, and we get 3r squared. But r is a function of time, so the chain rule says multiply by the derivative of the inside function, and so I multiply by dr dt, the placeholder for the derivative of radius with respect to time. So let's suppose that we know that the ball is increasing by 1,000,000 cubic meters per second. So dv dt is 1,000,000 cubic meters per second. And let's suppose at this moment in time, the radius of the fireworks ball is 40 meters. I can then replace the dv dt with the million, and I can replace the r with 40, and I will end up with this equation where dr dt is the only unknown, and I can solve for the rate of change of radius with respect to time. So doing the algebra here, notice the 3's cancel out nicely, and I get 4 times pi times 40 squared. 40 squared is 1,600, and 1,600 times 4 is 6,400. So our equation cleans up to be 1,000,000 equals 6,400 pi times dr dt. To solve for dr dt, I can divide by 6,400 pi, and when we divide 1,000,000 by 6,400 pi, we get 49.736, and the units are the rate of change of radius in meters with respect to time in seconds. So meters per second are my units. Notice the volume was changing by cubic meters per second, and when I divided by this number, I was actually dividing by square meters because I was dividing by radius squared, and so the square meters cancels into the cubic meters and leaves me with meters per second. So when our fireworks ball is exploding in the air, we can recognize that there's a good related rates problem in there. And in this case, 1,000,000 cubic meters per second of fireworks ball is creating an increasing radius of 49.7 approximately meters per second.